Okay, good afternoon, ladies and gents. Welcome to our second online technical meeting slot. We're glad you could join us this afternoon for an exciting presentation that Tshepo is going to give us on sampling stations. But before we do, I'd just like to mention make a few announcements. We will, as in the previous session, have a Q&A question box or Q&A box on the side. So if you have any questions, please feel free to type them in as the presentation goes on. We will address the questions at the end of the presentation. If I could please ask that you do not post questions under the anonymous mode. We would like to know who the questions are from, and if Tshepo needs to do a follow-up on the questions, he would need to obviously know who you are. So if you could please not post questions on the anonymous mode. So let me tell you a little bit about Tshepo. Tshepo is a consultant focusing largely on sampling and laboratory designs. He's got over 18 years of experience in the mining and engineering consulting industries, and he has done sampling and laboratory design experience in various commodities, including iron ore, manganese, potash, chrome. He has production experience at various organizations, including Hatch, De Beers, Kumba Iron Ore, and as an independent consultant. Some of the projects that he has highlights include the Kolomela sampling station at Kumba Iron Ore, Sishen QPIP, Colmag, Janssen Automated Quality Control Systems at BHP, the Iron Bridge project in Australia, and further work at Sishen. So without any more introduction, I think Tshepo's CV speaks quite extensively. I'm going to hand over to Tshepo.
Okay, thanks, Devresh. I hope everybody can hear me. Okay, so my presentation for today is on the design of sampling stations for bulk commodities. And look, I actually got involved with designs of sampling stations, I think or laboratories around 2009 or so, while working for Hatch, and we had to do a design for Kumba Iron Ore. And ever since, it has been an area where I saw that there was issues when it came to design of the sampling stations. So I took interest, and that's what I've been doing for the past probably 5 or 6 years, while on my own. But before then, I did it when I was at Hatch, and as well as when I was at Kumba Iron Ore. Okay, so I ran my company is called Measurement Process Solutions, and we specialize really in the design of sampling stations and laboratories, whether manual or automated. Okay, so for today, what I want to share is, the typical challenges that we come across when designing sampling stations, or even when clients operate sampling stations. And to say, look, what can we really do? What should we consider when we design sampling stations? Or if, sometimes clients they decide to do that themselves, that what should you be doing? What should you look out for? And then I just want to share 2 examples of sampling stations that we have designed based on the principles that I'm going to share, but although at a high level, I'm not going to go into the technical side of it, but still at a high level. And also I want to share the trends that I've seen in terms of how clients or product quality is managed. Because sampling stations and laboratories form part of the total product quality management. So in my experience so far, I have seen too many sampling systems that have become or are white elephants. during project stage, the client spends, or when implementing, they spend a lot of money on sampling stations, but you find that at a later stage, the sampling stations are sitting and they're useless. So, and that's one of the things that I saw. I thought, look, there's an opportunity that maybe one can engage or help companies at a very early stage to make sure that you don't find yourself with the situation. I think on top of my head, I can think of about 4 or so sampling stations or sampling towers that in the mining industry where money has been spent, and lots of it, and the systems are not working. Okay. So why is this the case that we find ourselves with such a situation? And my observation is that generally you find that sampling requirements are defined quite late during the project development. Instead of us starting as early as pre-feasibility stage to decide where are we going to sample, how are we going to sample, that is actually left until maybe even execution stage when I must say Iron Bridge is an example of that, where the guys are in execution, and during this execution stage, that's when we had to look at options of how are we really going to sample, and that has been quite a nightmare. But you find that ultimately you might end up with a solution that once implemented, you have to go back and rectify it at a later stage. And I've also found that there's a lack of understanding of the theory of sampling. I must admit, even for myself, I didn't understand much, and I took it lightly until I actually took keen interest and started studying the theory of sampling and getting an understanding of it's not as simple as we like it to be. It's not as simple as going into the plant, take a shovel and collect the sample, and you think that you have done a good thing. Also, I found that a lot of the time sampling stations are designed, implemented with inappropriate equipment or recommendations either by OEM or somebody within the organization who didn't really understand what is involved in selecting the appropriate equipment for the different stages of sampling. And one of the things in terms of that I've come across is where a lot of the times, because companies are trying to save money, they centralize the sampling towers, where they would say, look, we're going to have our feed and products being processed within the same sampling tower, only to find that at a later stage, there's issues, and then the client cannot do all the samples in that sampling tower. And the other thing is that I've seen that there's a heavy reliance on equipment manufacturers, sampling equipment manufacturers, to do the right thing. And I think that's where sometimes we go wrong. But ultimately, at the end of it, all the sampling stations, you find that they don't work because the client or the users don't trust the system. They don't trust the information coming out of it. So it boils down to trust ultimately. Okay. So what is it that one needs to consider when designing sampling stations? I think first of all is to make sure that we define sampling requirements as early as pre-feasibility stage. It might seem like no, sampling is straightforward. However, there is options that one needs to look at. Just like you do in the pre-feasibility, you come up with different options. Even in this case, there are different options that needs to be considered, and ultimately one needs to come up with a best solution, or maybe not necessarily best, but the optimum solution for the project. And I think just like also in projects where we develop the basis of design and we develop the design criteria, that's the route that we should take even when designing sampling stations. And when you put together this basis of design, I would recommend that one looks at the theory of sampling itself. You look at the ISO standard that are relevant to the commodity that you're looking at, because those ISO standards will tell you a little bit more about, I mean, you look at the lot sizes or the stockpile sizes that you need to build. It gives you an idea of how many increments that you need to take, and it gives you ideas of how the sizing of your samplers, especially the effective aperture size of your equipment. Also, I think one needs to look at, I mean, there are best practices that are there, and different companies have their own different best practices. It's important to look at those and rationalize and see that does those practices also talk to the theory of sampling and the ISO standard. So I think there is a sweet spot that one can find by actually looking at all this three areas. And then after that, I think the important thing is to define your sampling protocols. In a normal plant, you will define your process flow sheet, process flow diagram. So in this case, it's the same thing. Okay, you can look at it as your process flow diagram. When you say, yes, I'm going to take a sample, I need to split it, I need to crush, I need to split until I find I get to the final sample that I need to collect. The other thing is that, I mean, in defining the sampling protocols, one would be looking at the minimum masses that needs to be collected at different particle sizes. Okay, so if you take such information, the next thing I think needs to be done is to evaluate the sampling protocol using nomogram analysis, where now you would be taking that protocol, that flow sheet, you will be defining it as per the drawing that I show on at the bottom here, and where we actually define what is the fundamental error that we are minimizing. Okay, and this, if you look at it, for instance, it will show you this is the particle size that you are at. So it's different particle sizes. So if you move from the top one to the bottom one, that's when you are actually crushing. So you are changing the size of the particle. Now, once you have changed the size of the particle, you have an opportunity at that size to reduce the sample size to a minimum mass for that particular size. So that's what you would see here. This stage represents basically crushing to a smaller size and splitting. Now, also here, previously, the thinking was that we were allocating the same fundamental error to all the stages. So this graph would actually be touching that red line all the time. Now, the new thinking is that you allocate a fundamental error for the whole process, and then you start splitting that same. For instance, if you say 10%, then you start allocating portions of that 10% to different stages, with the stage which is at a higher particle size being accommodated the highest fundamental error. Usually at the biggest size, we would allocate 50% of the 10%. The next thing is that one needs to select the right equipment. I know in coal that you find that hammer samplers are popular, and some of the time they are popular because this has been they get selected at the later stage of the project, and you find that, look, there's no way of implementing a linear cross-stream sampler at the end of the belt to take a proper sample using that. I mean, but I know coal, they say it's okay, and I've seen lots of it in the other industries, but typically I recommend that we go with a linear crosscut. But for you to be able to do that, you need to be involved quite early on the project, so that you have enough headroom to be able to implement such equipment. And also then evaluate compliance of this equipment to the TOS, theory of sampling design principles, because the theory will tell you, apart from the minimum sizes, apart from the speed, it will be telling you the angles. It will be telling you, I mean, how do you you look at the different errors that are also there that you need to take care of in terms of the, designing the sampling station. So that is the other thing that I think we need to look at. But importantly, define the basis, define your sampling protocol, evaluate it in terms of nomogram analysis. And in terms of nomogram analysis, you would need to do some test work like heterogeneity test of your material to be able to use such a system. Okay. Then also what I've found is, as reference, Perigy's sampling theory and sampling practices by Francis Pittard. It's got a lot of information, very relevant, very practical information that one can use as reference in terms of the design. And then for the different commodities, like I said before, there is different standards that are references. But importantly, I think it's important that whether you are a client or a consulting company, that you do the calcs for the sampling station, so that when you get information or recommendations from the OEMs, that they can be comparable with your information, or you can cross-check that what they have done is similar to yours. And if it's not, understand where the differences come in. But those calculations you really need. You don't want to find that you expect that your sampling station at the end will give you a certain sample mass, but that's not the case. You find that it gives you far more sample mass than what you wanted it to do. Okay. So in terms of examples of systems that I have designed, this one is, I don't know if it's okay to share the clients, but this is at Kumba Iron Ore. In 2010 at Kolomela Mine, they had, when the mine was built, it had 3 sampling stations, and we had to go back later, I think it was 2014 or so, we basically scrapped the entire system and implemented this one that you see here. So this system is it was fully automated, because one of the things that you should remember is that, I mean, sampling is really on the low list or priorities for most people. And if you have a system, they expect it to just run. Okay. So it's important that we have such systems fully automated. The system actually collects interleave samples, and by that I mean it collects duplicate samples during a certain sampling period, whether you say 2 hours or 8 hours. In our case, this was collecting samples every 2 hours. I mean, a composite sample every 2 hours. I think it was sampling every 10 minutes. But so what it would do is that every 5 minutes it will collect a sample, and that will go. Those samples will go into different buckets at the bottom. So the interleaved ones, but at the end of the day, you composite those to make 2 duplicate samples. So such information or samples are helpful for you to, if you want to assess the sample preparation and analysis, that you can do a precision test in accordance with the ISO standards that are there. And you can be able to say, is this sampling station doing what it's supposed to do? And it can also help you to determine how frequently you need to sample, because if at a certain sampling frequency you find that the results are way too big, then it gives you an idea of the variability of your material. So then you would actually tighten or reduce that sampling interval. In this case, we went for time-based. I know that obviously the Rolls-Royce is the mass-based, but mass-based is not that simple to implement. And if you start by mass-based, it means you must follow it throughout, from sampling all the way to the lab. And sometimes there's mistakes done where there's a combination where people use time-based and mass-based in the same system. This one collected both PSD and chemical samples. It employs a linear cross stream as the primary sampler. We use a rotary tube splitter as a secondary sampler to produce both your PSD and chemical sample. And then on the tertiary application, we use a Vezin to both collect now the final sample for chemical and the final sample for PSD. All masses are recorded at each stage. So when we collect the primary increment, if you can see here at the top, there's hoppers, And I must say that, I mean, it all also depends how whether your material is clayish and all that you can use hoppers. In a case where your material is clayish or so sticky, we won't use hoppers. You do it directly on the belt, but there's recently belts that are on load cells for you to be able to record the sample masses. And it's important because, I mean, we designed this thing saying we're expecting a certain flow rate. For that certain flow rate, we're expecting it to take a certain increment. Now, can you actually confirm that that system is collecting the right increment? So by actually making sure that you've got bins on load cells, you are able to later on check the system and say, yes, at 1,000 tons an hour, indeed, the system collected this much increment. And you are also able to record the number of increments that you're collecting. All this equipment are on VSD, so that during when you commission it, you are able to optimize the system. Okay, and if feed rates do change, you are able to do that. Even we record obviously the conveyor feed rates, the cutter speed, the primary increment mass, the number of increments, the final sample mass that you also collect, because I think that is important to know how much mass did the system actually produce. And when the sample gets to the lab, did the lab get the same amount of mass as was produced in the sampling station? Because sometimes people take shortcuts, and I've seen it happen so many times where the sample is 25 or 30 kilograms or whatever, and because it's too heavy, the guys just chuck some of the sample to the side. And what you will see is that when you go to that sampling station, you'll be finding a heap of material next to it, and you wonder, what is that for? And that's when the people take shortcut, because the sample masses are actually not, they are heavy for them to actually carry to the lab. So you need to cross-check to say, okay, I got this much, and did the lab actually get the same sample mass? Okay. The second system that we have designed recently, and it was as a part of the proposal, but we had to actually go from not just the proposal, but to actually do a complete design of the system, develop the models for that as well, the 3D model for it. And this system, we designed it to sample on trucks, okay, coal trucks that gets to a power station. And then it consists of two aguas, and in this case it's rotating aguas, rotating cylinder aguas, as opposed to the screw type. And the idea with that was that we wanted to preserve the PSD of the samples. So what it does is it collects, once the truck gets into the station, it will actually collect, both aguas will go onto the truck, onto the trailers, and collect samples at the same time. In this case as well, we have a system to identify each truck as it comes in, so that we can say from which supplier the truck comes from. We have a barcode scanner there where the guy will be clocking, so that we can identify the driver. We take pictures of the driver, we take pictures of the trailers as we collect the sample, and those samples then are collected into a hopper at the top, combined. I think in this case, each agua was about 300 millimeters in diameter, collecting about 350 kilograms each. That sample then gets analyzed. So we have an online analyzer, chute analyzer on the system, as well as a PSD analyzer. And for this, the client actually wanted to make sure that at that specific point, once we have an online elemental analysis and a PSD analysis, this gets compared to the specification that was given to the supplier, and to be able to say, does it comply or not? So you can reject the truck or accept it. So that is still yet to be seen whether it will work, but that's the pilot stage proposal that we have. Okay, so the system also collects both PSD and chemical. In this case, I used linear cross-stream for both primary, secondary, and tertiary samples. And this is where it becomes important that when you do your own calcs, you'll be able to see which equipment, sampling equipment, will do the job. Because it's not necessarily true just where I would say, look, for primary, make sure that you use a linear. For secondary, use an RTS. For tertiary, use a Vezin. There are instances where you might find that, okay, it will work to actually use linear cross streams all around, or you find that, look, the number of sub increments that I need to collect at each stage are so high that for me to get the amount of mass that I need to have a Vezin in that case. Okay, so even on this one, all the masses are recorded, the cutter speeds, everything is recorded. And I mean, the idea of doing this is that, I mean, you need to be able to evaluate the system. You need to, like I indicated at the beginning, can I trust the system? I can trust the system if indeed it collects the samples that sample masses that I expected to collect. I can check through the system in that there's no blockages, cross-contamination. I think one of the things that we have on some of the hoppers that we even have cameras to check if indeed in between sampling that there is no sample still remaining. Although I mean we have those hoppers on load cell as well to confirm that. Okay, so those are the two cases that I wanted to share. I mean, there's more, but I think this just the two that I thought will be relevant to what we are talking about today in terms of bulk commodities. Okay. And then the trends that I've seen develop so far is that, look, as using conventional sampling or sampling stations, obviously it's got its own limitations. And the limitations are that you collect a sample, maybe you say over 8 hours, okay, or 2 hours. Then those samples needs to go to the lab, and then at the lab, it will take another 4 hours or so before you get the results. Now you have already 6 hours or 12 hours that has passed, then it's actually too late to intervene. Okay, so the trends that has been developing is that where conventional sampling stations then are supplemented with online analyzers to get continuous information on the quality of the product that you're producing. But I think one of the things that we need to implement is that when you do that, you need to actually also have a statistical process control that goes with it, so that you make sure that you don't intervene when you don't have to intervene. So that I think is one development or trend that not many are doing, but I think it's the direction that in the future most people will be adopting. And then in terms of conventional sampling stations, then we tend to leave them for your metal accounting samples, as in for your feed, your tails, and your product, just to make sure that, because we still believe those are still the most accurate way of collecting of analysis that we get. And then the other trend that I've seen is the use of online analyzers and development of algorithms to control stockpile qualities. What I mean is that you might find that you have maybe at the port where now you have to put or stockpile or put your material into the ship, and then you have different stockpiles, and you have to produce a product of a certain quality. So you need to draw from different stockpiles to be able to load that ship. So then you use online analyzers with algorithms in it on the platform. Then what you do then, you can be able to say, how much do I need to draw from different stockpiles of different qualities. And as you do that, it's almost like you have a target. And as the analyzer is analyzing, it will be showing you how you deviate from your target. And then say, look, for you to correct yourself, this is how much you need to be drawing from the different stockpiles. Similarly, if you're building a stockpile in a mine, if your process is you are able to change it, to control it easily, as you build that stockpile and you have a target, same concept will apply, where now you're looking at that and you say, okay, look, I have deviated from my target, but so far I have so many tons that I've produced. To correct myself, I need to start producing at a different, maybe at a higher quality or at a lower quality, to still be able to produce a product stockpile that is within spec. And I think that's really so far what I needed to share with you guys. And I am happy to take questions from here. I think maybe before then, I mean, I've come across this instrument recently, and it's specifically for coal. So it takes the same technology that you use on online analyzers, where you have a neutron source and as well as a detector, and it's able to analyze your coal. And all you need is about, I think it's a 1 kilogram of 6 millimeters. So instead of having too many instruments or preparation work, all you need to do is take your sample, crush it, put it in this machine, and you get your result. So I'm happy to take questions from here. Devresh?
Thank you, Tshepo. Very, very enlightening presentation on sampling, and I tend to concur with what you said with regard to the design of sampling stations. We've had instances where sampling stations have been designed at the later stage, and you end up having to retrofit them because they are showing bias or the sample cut is not representative. So fully aligned with that. And I think what you say with regard to having the design for the sampling station within the pre-fees is critical in terms of ensuring your sample representativity as well as engineering design, because you do need the headroom if you're going to do a cross-flow sampler. So fully aligned. From my side, I think what are some of the things that we need to consider on a pre-fees level? Obviously, the level of detail will be different to a bankable or to feasibility and implementation. But what are some of the key ideas or thoughts that we would need to consider in a pre-fees?
Okay, I mean, as said earlier, I mean, the first thing is, I mean, you need to look at the properties of the material that you're going to be processing. Like I say, is it a sticky material or is it a free-flowing material? And the options of deciding, am I going to have a centralized sampling tower, or am I going to decentralize it, where for either the feed, the ROM, all those, they have their own sampling stations, and from there you only collect the smallest sample that you take to the lab, or you're going to centralize and make sure that you're just going to collect big samples at each sampling station, and then go with that to the centralized sampling station or tower. And then you need to look at the different types of equipment that you have. Okay, look, I mean, if you look at the linear cross stream, for instance, you have to make a decision whether you're going to go with a bucket or you're going to go with a flow-through sampler. Okay, so and do those are the things that you need to look at and see the cost implication of the different options. And at this point, this is where you have an opportunity also to give input and say, if the process guys are doing analysis of samples, that sampling for, or let me say, test work for heterogeneity test work to determine your sampling constant, that can be done at that point as well.
Thank you. I see we've only got one question, but ladies and gents, if you have any questions, please post them. I think the one question we do have is from Lucky Swart. What is a typical cost for a primary sampling station? Obviously, I understand it's a very broad question.
Yeah, it's a broad question. Look, a typical, let's say we are looking at fines sampling station, okay? What I've seen, a fine sampling station at about 1,000 tons an hour system would cost you roughly about maybe 5 million rands. The whole system, all the equipment in there, as well as the controlling it, the electrics and stuff, but excluding the structure that holds that. If you look at the lump sampling station, it could cost you close to about 10 million rands. And if you go for a load-out sampling station, which is quite normally at high flow rates that you're looking at, so producing bigger samples, and because you also have lumps, you also have crushers involved. So there you could go to about 15 million rands. Okay, the system that I just shown now for trucks, that is quite an expensive one, because even on the cylinder, I mean the aguas themselves, you spend close to 8 million rands for one agua like that. So that system would cost you in the region of more than 80 million rands. Because it's got online analyzer, it's got PSD analyzer. There's just far more involved in that one. Yeah. Okay. Davraj?
Okay, I see we've got a few more questions. The next one I think is coming from Willem Slabbert from Multitech Sampling. If you do not have any variability data at the start of a greenfields project, how would you go about designing a sampling regime with liberation size followed by sub-sample composite size, given data for calculations is not available?
Look, and that's where, if you go onto the theory of sampling, there is a way where you can calculate like the sampling constant, okay? And that's the start if you don't have information at all. But if you don't want to go through the route of the theory of sampling, if you look at the ISO standard, it will give you the basic information that you need, because on there it gives you tables to say, look, at a certain particle size, this is the minimum mass that you need to be collecting. Okay, so that gives you at least the starting point of how to do it, and then that's why I say then later on, if you start early with this information, then later on you are able to say, look, I need 1, 2, 3 information. Then I start doing my sampling constant and stuff. But if you don't have it, there is a way of estimating it.
Okay, thanks, Tshepo. I think the next question we have is coming from, I think Willem has continued a question. I'm just trying to get to his question quick, if you give me a second. I think Willem's question is, furthermore, if the data is available from the geological work, the theory of sampling only applies to broken ores. Correct. How do you know the data is generated is reliable to start with if it is not done within a TOC compliant sampling plant, because the plant does not yet exist? Yes,
and this is I mean, this is where you start first with let's say if you do have knowledge, previous experience on projects, you would more or less know what to start off with. And yes, you might not get it right the first time, as early as that stage, but you can define just broadly what needs to happen. Okay, but then later on, unfortunately, you have to get this information of sampling constant to be able to get to a point where you come up with a system that you think will work. Look, it's a problem that is there in terms of geological samples. You don't have enough material. Okay, that's just how it is. So you can always assign a higher, let's say, a fundamental error to at that stage, just to accommodate that your sample sizes are just too small.
Okay, thank you. I think we're going to move to the next question. I think this one comes from Herman Oosthuizen. Good presentation. Could you please comment on the bias testing and confirming performance of a sampling station?
Look, it is. I've had discussions with Francis before, where he says, look, sometimes bias test is a useless thing to do because you might do a bias test and find bias, but you can do it the following day or so and not find the bias. So it's one of those things. But look, I can, without nothing being there, I think it is a good idea when you implement your system for the first time to do that bias test to check. And if you change something, if something changes in your process or later on, I mean, equipment gets worn and stuff like that, you can do a bias test just to check. But what I've found, and I thought it was a useless exercise, was that with the hammer samplers, for instance, the guys will come and they want to do a bias test. But when they do that, the first thing that they do, they'll make sure that the hammer sampler has got the scrapers are new and everything. And when you do that test, you might see that their hammer samplers are not biased. And I've seen this even at Kumba, where the guys, the Anglo research will come and do this work, and then they say, look, the hammer samplers that you have are not biased. They're okay. They're just as good as your linear crosscut. But those scrapers gets worn very quickly. If you go through and look at where hammer samplers are, in most cases you might find that there's also a lot of spillage, because as the unit goes through the material, it goes at quite a speed to scrape the sample from there. So I think it's one of those discussions that are still going around where people say, look, do we really need to do it? But my take is, do it when you think it is, and when you do it, don't get the system 100% and say, you know, if I change the scrapers and stuff, that it will be okay. But that's not where the system runs most of the time.
I think there's another question linked to bias, and that's from Henny Engelbrecht. Thank you, Tshepo. In executing performance testing, in brackets bias, on sampling systems, in what ratio have experienced the application of the 2-instrument versus the 3-instrument approach?
I'm not sure if I can clarify the 2-instrument versus the 3-instrument. Yeah.
I'm not sure. I think
Henny, maybe he can clarify that. Yeah.
And Henny, if you do require more, I think Tshepo's email address or the company website address is on. I think maybe just contact him directly. I think we've got one more question from Willem. Rotary tube splitters are inherently not symmetrical and therefore biased. More pronounced when you have a broad PSD, where the residence time through the unit is different for different particles based on their momentum, which is a function of their size. Did you pass a bias test around the rotary tube splitter in your first case study?
Look, if I remember, I didn't do the bias test on the RSD at the time. But yeah, no, I didn't. I didn't do that. We did it on the linear cross stream, and that's what we did. Yeah. But for me, there's I think maybe he's going into a much more technical point here. But look, for me, if I look at what I've seen is, I mean, if you look at a Vezin and you look at an RTS, a rotary tube splitter, I see those as two same units. It's just they operate differently. The other one, the feed, is the one that is rotating. The other one, the cutter, is the one that is rotating. Yeah. But I mean, it all depends. You can look, what we have checked previously was, I mean, for instance, if you look at the PSD, and normally we say the PSD is the first indicator of if there is a bias on the system, is that we checked the PSD of the incoming feed against the final PSD that we collected as a sample, just to as a quick check to say, I mean, is the system the complete system bias or not? Although I mean I understand bias. There's I mean, you need to collect a certain number of samples and do the statistical analysis to ultimately get to a point where you say it's bias or not. But yeah.
Thank you, Tshepo. I think very insightful presentation, as I said earlier. Thank you for making the time. I think, ladies and gents, if you have any more questions, I think you can get in touch with Tshepo directly. Tshepo, if maybe you can call out your email address for the guys that would like to contact you post the session.
Yeah, I mean the email is, as you see my web address there. It's Tshepo, which is TSHEPO .Molefe MOLEFE at measurementps.co.za. So you just take out the www and you just add tshepo.molefe at measurementps.co.za.
Okay. Thank you very much, Tshepo, for the presentation. And ladies and gents, thank you for joining us. Until the next one, thanks and have a good afternoon. Thank you.
Okay. Thanks. Bye.